All right, we are live. Where's Kat with our on the spot introduction to Aether Cosmology Roundtable 102? Thank you for the introduction. All right, we're going to be doing a review of cosmological redshift, which is the backbone of modern cosmology. What we'll find here is that a lot of what's put forward as evidence for the current cosmological paradigm is very circular, and each of these things become interdependent on one another in a way that they feel that they've built a cosmological ladder built on sound principles. So we're going to examine the backbone of said principles, see if we can get to the bottom of it. So this gentleman, we're going to follow the chronicles of Holt and Arp to get an insight of what it's like in the world of astronomy from the perspective of somebody who dared to have a different opinion or a different interpretation of the measurements that were being made. So to start us off, there's a couple of things that we need to familiarize ourselves with. There's objects in the sky called quasars. These are point sources of X-ray and gamma radiation, just high amounts of radiation. Now, they don't move, they're stationary points in the sky, and they have a high amount of redshift. So in the current cosmological interpretation, it's interpreted that these objects came first. They don't really know what's at the center of them, what's producing the source of the radiation that they're measuring. There's several hypotheses, but none of those are particularly important. The important part is that there's objects in the sky that have known coordinates, known celestial coordinates that you could look up, and you could, if you had the right instrumentation, you could see these radio waves, or you could see the energy emissions from them that aren't coming from the visual spectrum. So we're going to go over all of that as we continue. So why is redshift so important? Well, it's the backbone of astronomy because from redshift, you can determine, because all redshift, when you hear redshift and blue shift, all you need to think is Doppler shift. So when something is moving, there's a frequency shift that's proportional to the velocity. That's so the principles that are measured in the lab and are known terrestrial effects are being applied to the sky. So when they make measurements of light spectrums, there's a redshift. So they interpret this as a distance and a velocity through some additional hypotheses / laws, like they call Hubble's law, Hubble's constant. These sort of things are proposed to make distance and velocity equivalent to support the cosmological paradigm of infinite expansion due to a causal mechanism of a Big Bang. All right. All right, so now we're going to look at some of the stellar objects that ARP was finding in the sky and how they were contradicting the current mainstream model. Because the important thing to note is that in the mainstream model is that all the objects in the sky are not interconnected. So just because you see a galaxy and some stars next to it or some bright things emitting energy from them, they couldn't possibly be connected, although they're perceived to be on the same plane. Because when we're looking at these types of images, right, you can't tell any depth to them. You can't tell if this dot is in front of this dot or behind it, or if they're on the same plane, right? So this is all. Go ahead. So, so so what they would do, right, is like this galaxy, right? These are all related, but like probably 100,000 light years of distance apart, right? But then as you get further out between these distances here, like the distance between this galaxy and this is unfathomable. There couldn't possibly be an amount of physical material or energy that connects these two in the sense of a bridge. So what would have to be is that this wouldn't, or this one, pick one would have to be further back than the other. And what we're seeing is just like an overlap of that. And it's not necessarily that they're connected. It's like, is the way that they want it to be perceived. Yeah. And then so if we look over here on the right too, on this one, we see, this dot right here, like this shouldn't be connected. They would say like that the distance between this black dot and this like disk right here is like it's unfathomable, man, like light years, right? But when they start looking at it in different spectrums, they find that it's either connected by, what they would consider physical dust or gas, or it'll be connected by a stream of radiation, which it couldn't possibly, like, it's not supposed to be. Yes. Oh, shoot. Okay, one second. I'll fix that. All right, sorry about that. So Shane was asking about the interconnectedness of the galaxies and the stuff nearby. He was asking about, like, isn't this connected then? Well, and and that's where I was explaining, like, the distance between this dot and this galaxy structure here is like an unfathomable distance. It wouldn't be considered to be physically connected to this in any way. But then when they start looking at it in different spectrums, they can see that there's like a jet stream coming out of the center of it. And it looks like these galaxies are ejecting the quasars, like birthing them, so to speak, rather than there's some distant object that is further behind the galaxy itself. Little stellar birth. So now we're going to look at some images of said stellar births. Now, like I said, the interpretation of what these are is, anyone's guess, right? They've got their own interpretation, but we're just going to look at the cool images that are up there that other people have also used their own instrumentation to confirm. So when we get into the visual aspects of it, like, other people have observed these with their optical equipment, and then at the professional, radio astronomy level that ARP was at, you can analyze these same images in different spectrums and stuff. So that's where you get like a difference in the readings there. But these are all things that are mapped out in the sky, and you could presumably use your telescope and find them. So here's just some cool images that we're going to look at. And these are named after ARP. So he's got like 30 or 40 different stellar objects named after him. Like, he was a pretty famous and important astronomer in cosmology. It wasn't until he came up with a different interpretation of the redshift based on what he was observing, where he became excommunicated for that. So these black and white images here are images taken from amateur astronomers with their own equipment. So they, tuned into these celestial coordinates and observed the same objects that ARP was finding in the sky. So the difference here, right? We have images and things that people can observe in the sky for themselves with their own equipment, versus getting data from like the new what is it, the Hubble telescope, right? Like, nobody, like, they say that the way that they're looking out into the spectrum of light and all that, like, nobody else could do that. That's completely unique to their own thing. So like, if they're simulating things and doing their own interpretation, we wouldn't be able to know or confirm that. But what I like here is that all of ARP's work and ARP's interpretations are confirmable by other people's observations. So that's extremely important. So here's just more of the same. We're almost done with these. Wanted to give some nice things to look at before we get into some technicalities. All right, there's the end of that. So we need to understand the scale of the units of measurement for what they're putting forward. It gets quite astronomical. Dad joke, pun intended.
GU right there?
No, this is one
GU. Oh,
no, yeah, this is nah. Yeah, this would be some amount of parsecs. Anyway, so 100,000 light years would be the length of the Milky Way, right? But to kind of break it down, to start from scratch, to get a real grasp on that, we're going to do light coming from the sun, in their cosmological model, traveling at the speed of light. So in 1 second, a photon, or a wavelength of light emitted from the sun, will travel 300,000 kilometers. If it travels for 1 minute, it's going to go 18 million kilometers. So this distance scale is increasing here, not quite at Earth or anything yet. At 1 light hour, it goes 1.8 billion kilometers. So we're getting further out now. We've now passed Jupiter in light traveling for 1 light hour. In 1 light day, we get 25.9 billion kilometers. So now we're way out here, but still nowhere of significance. And then 29 days of light travel, as Shane called it the other night, a what was it?
Light month.
A light month for the moon. Yeah, for the photon. So after a light month for the photon, you're going to be out here at the Oort cloud. And then over a light year, you're going to have traveled 9.4 trillion kilometers. Very, very large amount of distance there. Then what they've come up with now is that the nearest star is 4.25 light years away. So that's to kind of give you the scale here. So even after traveling for 1 light year, you would still have a much greater distance to transpire to even get closer to the nearest star, is what they would want us to believe. This is how this scale works. Now, the cool thing about this scale, like if you ever wonder, like, oh man, the space time and all this stuff, like this is the way that they have these distances, and the way that it makes sense in their cosmology is that it's just a infinite section slice of a manifold. So this grid here just goes on forever, and then it's just locally flat, and then they would impose math conditions on it that would describe curvature within it, and then they would have another tensor to describe motion along said curvature. But that's like what we're looking at here is just an infinite grid made out of multiplying space and time together by infinity, and they get these, they have an infinite section in which they can build their whole cosmological system on. So in this scale now, if you were to travel 100 light years, you would travel 946 trillion kilometers. And again, looking at the full distance of the galaxy to traverse it end to end would be 1,000 light years, which would be 946 quadrillion kilometers. All right. Now, another thing that they introduced, because this gets ridiculous, right? When we've got this infinite scale here, we can't be notating things in millions of light years. That looks ridiculous. People would start questioning things. We need another unit to tie it to. So we're going to tie it to an angular measurement as well. So we're going to say that 1 light year is now equal to 3.26 light years. And the way that they come up with the angle relationship to it, they're going to convert 1 arc second in the sky to a parsec, which is the 3.26 light year conversion. So if you were to kind of think about this in terms of if you were far enough away from the Earth and the sun, they would appear to be closer together. And if you were so far away that the distance, like in their model with the sun being 93 million miles away from the sun, if you were to be so far away from them that they were only 1 second apart angularly, which, definitely, Shane, how funny is this? To get that, to cause that to converge together, you would have to say that, like, visual space isn't Euclidean, because otherwise why would they converge into a parsec, dude? That's hilarious. But anyway, so as you get further away, the sun gets closer to the Earth gets closer to the sun angularly, and when there was 1 second of arc between them, that distance you would be away would be 3.26 light years. So that's what that would come out to. So that's what they've related in terms of distance to an angle there. And now we can talk about things in terms of a distance without involving light in the way that it becomes like, what, light year? What's that? Well, now we have
help to make things when you're talking about made up stuff. Really big numbers do help to guise it. That's a good point, Shalom.
Dude. Yes.
Like when you're gonna lie big or whatever.
I can see people's microphones going off. Are other people talking?
So hold on, no, but he was stuck on he's still stuck on. I don't know what's up with that.
Okay.
For some reason.
Oh, there we go.
Good, Ned. You fixed it.
So we got our unit of measurement, which is definitely not dependent on non-Euclidean visual space. And then now we need to talk about how they get a distance out of brightness of stars. So they have 2 ways to classify brightness. That's the visual magnitude and the apparent, and the absolute magnitude. So the absolute magnitude would be how bright the star would be if you were to observe it from 10 parsecs away. So its real magnitude is obviously going to be less. And the way that they've come up with the scale is it's logarithmic and backwards. So the lower the number gets, when you get into the negatives, that's when the stars are the brightest. And when you see the positive value, that's when they're not as bright. So what we would terrestrially see if we were Nicki Minaj with our telescope looking out at the star and we said, okay, its brightness is 3, when we did the math transformation in comparison with their logarithmic scale, we would say, okay, well, now we're going to transform to a distance that's 10 parsecs away, and that would change the magnitude of this star based on that change in distance to this right here, and it's going to be 0.8, and that is going to make it much considerably brighter than what it is at the 3 magnitude. And remember, it's a logarithmic scale, so it doesn't change linearly. So the difference between even 2 and 3 is orders of magnitude. So when you get down to a difference of 2 or 3 or greater, then that's orders of like just insane, unfathomable amounts of brightness. Like we get into some of the numbers that they would produce are like -13, -20, just insanely bright. Now, after they've derived the difference between the absolute magnitude and the apparent magnitude, they can use the inverse square law to backwards derive what the distance would be to create the radial fade off of the light for you to absorb this 3. To make this 3, how far back would it have to be 8, right? So like they just inverse square it back to the light source. And an important thing for them to do this was to use pulsar stars because they have a pulsation rate. So they go through periods of brightness and dimness. And so what they would do is they would watch these pulsars for 90 days and do the average of their brightness and take that and do a bunch of calculations to turn that average into their absolute magnitude over the distance. And then they just inverse square it out. And it gives them the actual, in their model, the true distance. Dude, I know it gets crazy. They also get how much the star weighs off of that.
So one of the star twinkles a little bit overnight, and they watch that twinkle for 90 days. And from that ratio of dim to light and luminosity, they contrive a whole distance-based algorithm, which then gets used as a standard metric of measurement to determine distance.
Yes, sir.
Wow, that's science right there.
Yep. Right. Another aspect of what we need to know is how they analyze light. So we can think about light in this conceptual model here, where wavelength and frequency are shown here. The crest in between the waves represents a wavelength, and the amount of crest and troughs in one cycle determines the frequency. So if this frequency was high, let's say this cycle here was from this section to the beginning section here. If there was more peaks and troughs in here, or crests and troughs in here, then that would be the high frequency. But we only have a couple here, so you could think about that as like low frequency. Now, let's see here. The distance between wavelengths is measured in the wavelength of what the radiation is that's being emitted. So the distance will be relative to that wavelength. And so based off of that, they've categorized, all different forms of electromagnetic radiation into, different wavelengths and frequencies based on these wavelengths per cycle, and a cycle being defined as 1 second. So when you look into quantum mechanics and black body radiation from Planck and the equation he used to describe that curve to relate temperature to relate color of a star to temperature, all of that comes off of a 1 second cycle. It's all bound to 1 second. So however many peaks and troughs there are in 1 second determines the frequency. And that could be also considered like how much energy is in the wavelength. So the more oscillations per second, the more energy it takes to create that. Okay. Now there's a whole spectrum here. We got the visible spectrum here. So that's where you're going to actually see the stars, and they're going to flash and have different colors and whatnot. And then when you get into these other spectrums here, that's when we're going to have to use radio frequency equipment to analyze the spectrum that the stars are emitting out. And so when we look at those black and white images and we see, see if I can find a couple here. They're in the back, but anyway, those black and white images come out of that measuring those frequencies. And then when they apply false color to them, like in this image here, they're just applying arbitrary colors to different frequencies to kind of give you a visual representation of what it would look like if if these colors were visible to us. So that's kind of cool. We get these nice artsy pictures here, but traditionally, you would obviously see them in black and white. They would have no color. Okay, so frequency and wavelength, which we went over here already here in 1 second intervals, the crest and the troughs for the waves. And then Lord Kelvin, of course, came up with the scale for relating color to temperature. So we have his scaling system here. So when you look at a star and it's yellow, they hypothesize like, okay, it's this color range, so it must have this much energy, and then they start coming up with how much what chemical compounds would be burning to produce this, and that's how they come up with what elements are in the star, and they have different classifications based off of that. So if it's like this color, it'll have these corresponding elements, and it'll be this classification of star, and they've got these all broken down into the different color bands essentially, and that's how they get to producing things like the elements that they're made up of and how much they weigh, because once they've determined their pulsation rate, they can they make up a story about how much gravitational force that would take to to produce that, to trap the element that's causing the corresponding color shift and all of that. So it just becomes a very circular, like, oh, well, if this is what we see, what would it take to produce that under these, under these conditions? And they just kind of algebraically fill in the blank, because that's all it really is. When you know one of the other two of the other variables, you can just solve for the last one. So to get into emission and continuous spectrums and absorption, what you can do when you're looking at starlight, when you're splitting it into a prism to examine those wavelengths, you can also do spectroscopy readings on them. And what that is that's basically the way that it's done terrestrially, right? You would burn a certain element or gas, and then you would look at it with a spectrometer, and you would see the emissions of the elements that get absorbed because they have the same energy amount. So once you know what's missing from it, you can identify it in the color spectrum, and that element produces that energy, that wavelength there. So once they started categorizing all of those terrestrially, they came up with the absorption and emission spectrum lines for all the various gases and elements and stuff. So they had quite a known extensive log of terrestrial measurements here. And then when they look at the sun, they get a continuous spectrum here, which is different from the other spectrums because the lines, there's no absorption lines here. It's just it's a fading gradient, and the sun is the only object in the sky that produces that continuous spectrum. All of the other stars, which are said to be, just like the sun, have different absorption and emission lines. And now in terms of what causes the absorption and emission lines, who knows? It's anyone's guess. So there could be those elements up there and all that doing that. And I don't really know, but the important thing is that other labs, look up and do the same thing, and they see the same missing lines. So they're drawing the conclusion that, okay, well, therefore there must be something in between there, like this gas cloud, etc. But that is essentially what they're doing, and they're just drawing conclusions from that. That's how that works. Now, in 1922, an important cosmological factor was introduced, which is the Hubble constant.
So did anyone ever corroborate that colored Kelvin scale, or did someone just say that and then everyone went with it and built upon that as if it was true?
It's a good question. It's just kind of rearranging the regular temperature scale. So like in terms of, that ratio, it's just a ratio of constants. So I'm sure it's fine, dude.
Well, because they got a ratio for distance based on the twinkle rate. And now they got a ratio for the heat and the energy based on the color spectrum, which two things that no one can ever corroborate or like anywhere. They just, and then from those two presuppositions, they build upon a further like a presupposition and then a
Yeah.
further layer, and then no one ever checks any of it. No one could
N-
ever possibly corroborate. This is
No,
crazy.
no. So the Kelvin scale started off good, right? Because what he was doing was terrestrially measuring. So, like Newton figured out, okay, we can split light from the sun into different colors. And then Lord Kelvin was like, okay, let's measure each one of the individual wavelengths. So we put thermometers in each one of the split light bands of their respective colors, and they all had different temperatures. And he compared them to ambient light in the background that wasn't split,
Yeah,
and then
isn't
also
that
one in dark.
terrestrial spectroscopy?
No, that's what I'm saying. It started off with like an actual scale of like meaningfulness, but yeah, it's been extrapolated out into the cosmological grand scale. So like obviously no one's confirmed that, but it started off with like, you know, a nice noble intentions. So Hubble came along in 1924 and introduced his cosmological constant, which was that redshift is, or that the velocity measured in redshift is proportional to distance. So this is where now they're starting to relate the like depth to these pictures. So we looked earlier at all those black and white images where we couldn't perceive any depth to them, but now they can. Now they're interpreting the depth to the pictures as distance based off of the redshift. So when they see the redshift, they're like, oh, well, you know, how is that created? Well, the distance between them, because there's what you would consider what you would intuitively think as the galaxy moving, having a velocity, but that's not actually the way that they want you to conceptualize it. The way that they present it is that the galaxy is moving due to the expansion of space. It's being carried along due to the expanding space, which for them is purposely distinctly different from the galaxy itself moving with respect to space, because one of those would imply absoluteness, a center, a radial center, etc. So the difference there by separating them might sound like counterintuitive, and it is, but it's very purposeful because it needs to be distinctly different from anything that would lead back to a radial center or being relative to an absolute space. So if the space between everything is all relative, then that gives them more leadway, more credence to their relativistic paradigm, because it's in line with, you know, no absolute time and space. All right, so he went through a series of measurements of different stars doing, we talked earlier about the pulsars. Well, he pioneered this pulsar method of relating that pulsation rate to a distance. So here's what they would say is a Cepheid, and this is just a star that pulses. I like the term pulsar better because it's Cepheid sounds insane. So we're looking here at a star that's pulsing. And that's what we talked about earlier with the pulsation rate over 90 days being monitored, averaged out, and then determined, you know, how bright would it be if we were 10 parsecs away from it. So that kind of thing. Now with that, we're going to look at the math used to interpret the redshift, because what it shows here is that they're just doing a V over C relationship. So they're just comparing the measured wavelength of the starlight to the lab wavelength here, noted by lambda naught. And then it's over lambda naught to normalize it. And what that does there is it just reduces to V over C. So the ratio in which they're using absolute velocities but they again believe in a paradigm where there's no absolute velocity. So they change it to, you know, it's the distance between space, or the expansion of space rather. So this is how they come up with all of that, by just using a simple V over C relationship. So when you see the Z here, when they talk about redshift, it's just a ratio of V over C, meaning the difference in frequency shift for the measured starlight versus what's measured in the lab when there's no movement. In that ratio difference, similar to interferometry, like when they take the square of the distance between the fringe pattern. Well, when you ratio that with the wavelength of the original starting wavelength, that gives you a velocity component that's proportional to the square of the fringe. So like similarly, they interpret the fringe, with respect to the laboratory measurement, and they go, okay, it's moving this fast. There's this much. This is how much expansion there is, and that's also the distance between the stellar objects. So if something has a high amount of redshift, the interpretation is that it's super super far away, and in their cosmology with light travel, having a finite speed, that also gives them an estimation on the time scale. So like how long ago did this object exist for it to be that far back because of the expansion rate at this particular rate. So that's how they come up with all of these things here. And similarly, terrestrially, right, we have GPS showing the frequency, the Doppler shift in a moving object. So GPS will tell you, it'll derive your distance and velocity accurately, and it does that through accounting for it with a simple V over C relationship. So we have V, your V car over the wavelength, and that's literally just V over C. So the maximum Doppler shift frequency that this observer is going to receive from this satellite here is going to be directly proportional to his velocity, which is interpreted in the mainstream as the speed of light is constant, but the wavelength shift is just something that happens mechanistically for the observer, but the speed of light is still constant. Now that doesn't make any sense because GPS is a timing interval system. So if it derives distances based off of timing differences, and there's also a proportional velocity shift in the frequency, well, then that's just C plus or minus V proportional to the velocity of the receiver, which is classical mechanics holding true terrestrially with electromagnetic radiation in velocities that are going in all different directions. This car doesn't have to be going in a circle for it to be relative to the radial center of that to make the velocity measurement. It just is what it is. It turns out that this mechanism exists for electromagnetic radiation, and the principles of relativity, which say that this measurement shouldn't exist, aren't true. And so doing this relationship the way that they've described described this velocity as a expansion between over distance rather than a velocity of an object is how they, preserve their relativistic ideals. All right. Now, earlier when we were talking about the pulsation rate of the galaxy, of the pulsars, you can also relate that to how much gravity and how much mass the body has, because what they would do is they're saying, okay, we're looking at this star, it's this color, therefore it has this much helium, and the brightness in its atmosphere, the pulsation is caused by the helium not getting fully ionized and being able to escape the gravitational pull. So it goes through periods of creating like a blanket of helium, and it becomes opaque, so it dims the starlight coming out of it until enough ionized radiation fills up and it bursts out and gets ejected, and then that's when the star becomes brightly lit. So through this, they determine how much gravity it would take to hold in that amount of helium to create that amount of brightness. And they just, right? And they just do a little shuffle here. Suddenly, the mass and the gravitational potential. So very cool. Based off of like a density relationship.
Yo, you know what that reminds me of is what Cassandra said the other day when he was making the observation that, the constant in Kepler's third law, if you do like t squared over a to the third, right? Because it's using the constant, which is the derivation 4 pi squared over g m plus m, which he's like, his argument is that the sun's mass m is losing tons per second, so it's actually changing, and so it's a constant that changes constantly. And what happens with that as well, they say actually it's not that it's changing. We're going to keep the g constant in that formula, but what we are going to do is we're going to adjust the semi-major axis A and the period t to adjust as the sun loses that mass to keep the law balanced and everything constant. So it's like, oh, it's C is really C plus V, but we're just going to pretend that it's C all the time and make adjustments as we go. And they're doing the same thing with this luminosity distance scale, it seems.
Well said. And yeah, dude, that's hilarious what Cass was pointing out. I was always wondering about that too. And he's just like, yeah, they just, as it loses mass, it just pulls it in a little closer because it can't get out as far. And it's like, oh my God, dude. They're just, they just keep the same proportionality the whole time. Like, come on, man. Come on.
We're proportionally fallacious.
Dude, as long as they're proportionally fallacious, it remains invariant. So
There you go.
it helps them out. So the summation of all of this is that it leads to a possibility of a Big Bang cosmology where an explosion out of nothing, where the space in between is all physically meaningless and expands due to, a mechanism of dark energy. This is the only way that they could get there. So this Big Bang happens. This radiation starts to cool down. As it starts to cool down, it starts to form elements and material matter. The material matter starts to cling together due to the gravitational forces that are created by, quarks and bosons and Einstein, whatever they say, whatever they try to get the cause of gravity as. But anyway, all this stuff starts clumping together and it starts getting hot because when things clump together, it gets hot and it also starts rotating. And then then with the friction from that, it becomes a star and it gets bigger, starts consuming more stuff around it, becomes a galaxy, starts ejecting out a bunch of energy, it makes little companion galaxies, et cetera, et cetera. And all of that comes from nothing. But to get there, right, you have to have a framework of interpretation of which this would even be possible. And that would only be possible as if your interpretation of starlight was that meant that the distance between everything in the sky was expanding 4 times the speed of light, essentially, but keeping it such that the light that you do get coming in has been traveling for such a long time that you'll always infinitely see it in perpetuity, even though the distances are expanding forever.
That was a really good summary of the universe and how we got here. Really backed by science, and I truly believe that now.
Like before I started this Prezi, I was a little skeptical of what they were putting forward, but when I say it like that, I mean, I'm kind of like, if they had said that up front, I would have been like, all right. As long as I know, as long as I know what I'm signing.
I just needed the visual map to show like where it starts, like where we came from and where we're at, and that really puts it in perspective.
Like right here, there's nothing, no
right
purpose, no design. So like if you've ever looked at a DVD player, a car, and went, oh man, I wonder who built that and made all the parts and constructed it and designed it and came up with the schematics and gave purpose to it. None of that would be here. There would just be apps, just nothing. And then
look at all that nothing before it became everything that is. Right there, the next line is everything.
And then suddenly everything. It's like suddenly there's a DVD player over here. So we went from nothing to DVD player. And how did we get there?
Or whatever.
How did we get there, of course? Well, introduce Einstein's field equations. Now, most people don't really do anything with Einstein's field equations because there's only a handful of solutions to them. And one of them is explains our homogeneous cosmology that gives the possibility that this explosion could happen. And then supposing certain conditions, which we'll go over here in a second, that this would homogeneously fill out and cool off and, make everything structured in the universe out of complete randomized nothingness. So let's go over what all that means. Starting from the right to left here, we're going to go T mu nu, which is the energy conservation tensor. What this does is this conserves energy and momentum into a gravitational field, which is going to curve space-time by this coefficient over here, which is 8 pi g over c to the 4th. And what this is doing is this is creating a 3-dimensional sphere in space with the 8 pi. So that's the geometry for a sphere. And then it's going to distribute that over the gravitational constant there over c to the 4th. And by bringing it over c to the 4th, it's making it so that it requires a tremendous amount of gravitational influence to curve space-time because you have to overcome c to the 4th there. Then as we move on to lambda g mu nu, we have the cosmological constant, which we'll come back to in a second, but this is what describes dark energy. So this will also be relevant to influencing the curvature of spacetime. The g mu nu here is the spacetime curvature. So this describes how spacetime is going to curve in the presence of this gravitational field that's been conserved, that's conserving the energy and momentum of whatever. Now, over here, we have the Ricci tensor, which is describing how an object is going to travel along the curvature of said space-time here. So these are how all these equations relate. And these notations here are tensors, which describe matrices. And in these matrices, you set the conditions for what you're going to, or how you're going to solve these tensors, how you're going to calculate these out. So the important part here is we have a it's kind of, you can think of this as kind of like a shell, a framework, a manifold, right? Well, that's exactly what it is. You can think of this as an infinite manifold. And when we put in these conditions here to solve this, we're taking a slice out of that manifold and we're looking at, like just a small section of it. And we can describe any distance, anything in this manifold because it's infinite. It's a manifold. So this is how we solve said manifold, by assuming conditions and imposing those on the manifold so that we could solve for it. One of those conditions requires there to be a perfect fluid. So we've all heard the term, hey, the universe is homogeneous. I can't, and we know it's homogeneous. In the way that it's prefaced too is that we know it's homogeneous, and we know it's not perfectly homogeneous, but like it's pretty close. Guys, that's a ruse. It's perfectly homogeneous. It has to be, because to solve this tensor out, they have to use an idealized fluid, which it doesn't say that this is an almost perfect fluid. It's a perfect fluid. It's idealized to be exactly perfectly homogeneous to create an even distribution as everything expands out and cools off. Otherwise, there would be chaotic clumps of everything, and nothing would, there would be patterns that aren't observed that are observed here. So to create the illusion, so get this, right? To explain why all the observations make it appear that we're at the center is that there's just infinite expansion. But to facilitate said infinite expansion, you have to assume a homogeneous medium to facilitate the growth of the infinite expansion, so that there's no chaotic order to the evolution of the material matter as it expands out and cools. So it's preposterous.
If it was exactly precisely homogeneous, no galactic accretion would ever occur. No dust particle would be any further or closer than any other dust particle, thus would not attract. Crazy.
Yeah. And then so get this too, is like these conditions imposed here, there's like a couple other ones they can do. And then there's different settings for like values that are like in the universe. So like, is this universe empty? Is there one object in it? Is there a black hole in it? Like each one requires its own specific conditions that aren't even in the same universe, so to speak, right? Because these are non-linear field equations. So you can't be like, oh, you know what? We're solving this cosmological issue here, and then we're going to add a black hole in it with this metric, with this other metric. That's not how non-linear field equations work. You can't superimpose on them, meaning like you can't just add to them. So each one of these tells like a different tale to a universe that has nothing to do with what we observe. So that's cool to know and understand. But anyway, in doing this, to create all of this, they actually have to violate energy in their momentum tensor. So they violate global energy and momentum conservation to even solve this, and they're all completely fine with that. So to even start off this untenable position of everything coming out of nothing in this idealized fluid medium to create homogeneity as everything cools off and becomes material matter, it's not even tenable by their own standards of physics, where if you violate conservation laws, you're not doing physics. So that's a cool exception that's a cool special case that they made so that they could even attempt to use these equations to dazzle the public. But as we go through the metric here, like I said, there was a couple of different conditions you could impose to solve this. So you can describe a closed system, you can describe a flat system, or you can describe an open system, which describes the infinite expansion there. And out of that, you get two time derivatives. The first time derivative for velocity, and then the second time derivative for acceleration. So when they talk about the acceleration of the universe, that comes from calculating out with the negative one here when they fill in what they need to for the tensor, and that gives them their expansion there. And then back to this cosmological constant here, this lambda. Well, it turned out that when you solve these field equations based on the conditions you impose, if you do infinite expansion, if there's nothing to keep it from collapsing in on itself, the equations predict that it will collapse in on itself. So the only way to stabilize it is to introduce this lambda here, which is the cosmological constant. And then Einstein went through a phase in his life where he didn't want to introduce it, said it was not needed, and then they discovered that they needed it to it gets insane. So whether or not this is here or not, they just they need it now, so it's in there. So this represents the energy necessary to facilitate the expansion without it collapsing in on itself. And when they talk about, when Michikaki's like, oh, we're off by 10 to the, negative 120 on whatever, this is they're off by the amount of energy required to facilitate all this. And it's like, they don't care. They don't care because they know that most people don't understand it anyway. And like, surely somebody else will figure it out. All right. So there's the time derivatives for deriving the constant expansion versus acceleration for the expansion. That's where all that comes out of, after assuming, all those conditions. All right, so that was very cool. So quick recap here. Experiments with light resulted in highly precise categorizations of temperature and color and wavelength and frequency. Comparing light from celestial bodies from those same wavelengths measured in the lab shows a shift, and from that they're interpreting that as relative motion. And to facilitate their cosmological principle, instead of having it be relative motion, it's relative expansion. So a huge distinction is that their cosmological redshift does not imply relative motion for them. It implies relative expansion. So that's very cool. They came up with a way to relate the apparent magnitude, what we visually see of a star, to an absolute magnitude, which is an idealized, which invokes a transformation to a fictitious observer who's 10 parsecs away from the star, which would increase its brightness by, several magnitude. And then they calculate out from there the differences to create that distances to trace it back to where the star would actually be as a true distance relative to the observer to see it at that original magnitude using the inverse square law based off of a fictitious observer in idealized conditions to change the brightness of the star. And if anything's wrong along that cosmological ladder, then the whole thing is wrong and none of it has any physical meaning. So we're often confronted with like, tell me where the distance to the star is. How far away do you think the sun is? And like, none of it is meaningful. It's only meaningful if relative to the conceptual model you're talking about. So if you're talking about the distance to the sun and the conceptual model of how to navigate on Earth, well, then the sun is the same distance as the radius of Earth because they use a celestial and terrestrial sphere model where one overlays the other at the z-axis. So
but they're also just using ratios, as we see with every single step of the way. They use the wavelength ratio to get distance, the luminosity ratio to get and then they use that to get heat, and then that ratio, just like with Kepler's laws, a ratio and like an observation of a periodicity. And then it turns out that even when you change one of those things that can't change, like mass, then everything else just changes around it, as an algebra equation will do, to sort the rest of it out automatically. And they rely on that super heavily on every aspect of the way, which is amazing.
Yep, and none of it's ever wrong. It's all correct. And like that's why when it's put forward as like a cosmology and also mixed with physics, they can't go back on it and be like, oh, you know what? We were wrong about this because they've like merged cosmology into the realm of like this is physical reality, right? When we look up at the stars, we're not looking at the heavens. We're looking at a bunch of rocks and dust and stuff that all clump together from what we hypothesize as an explosion of nothing. That's our working theory, dude. Imagine you showed up on some dude's island and you were like, some civilization's island, first undiscovered or whatever, and you were like,
you're like, what do you guys? I figured it all out.
You're like, guys, what do you think is going on up there? And they were like, oh, you know what? Everything up there, the distance between it is expanding forever, and it came from nothing. You would be like, oh, you guys ain't right. But like this is mainstream accepted cosmology because it's presented as physics through the circularity of the ratios.
The response is, so when are you throwing the Virgin into the volcano again? When was that?
It's like, what keeps the sky from falling? Sacrificing people at the altar? It's like gravity. I had never heard of her. I do, however, have a collection of people to throw into the volcano to stop it from. Anyway, so we're going to close out on looking at some cool colorized images of the objects that ARP discovered over the course of his career. and how they are
ones that are definitely not connected, though they look very
yes,
connected.
and how they are
Okay.
super connected / not connected because after everything we went through, right? Remember how important it is to have nothing physically connected, have vast infinite distances between everything so that nothing's actually physically meaningful. What ARP was measuring and looking at was that these things were actually interconnected, but via either what they would consider dust or streams of energy. And it appears that, like I said, the highly shifted quasars that are emitting, way more energy than the galaxies, they should be behind them and whatnot. But it appears that that they're connected to them via the streams of energy that are ejected from the center of the galaxy and spiraling off and stuff. So we'll go over some of those images and whatnot, and some of the points of contention that were brought up to ARP. But because he had the credentials to actually challenge mainstream cosmology, they had to silence and censor him. So when he was trying to publish papers on these and explain his position, because he has a different interpretation for the redshift. He thinks that redshift is an intrinsic property of the formation of matter. He thinks that the galaxies are basically, creating these quasars, which are like young galaxies, and they're going to eventually become their own galaxies as they mature. And as part of their maturing, they go through this redshift process where it goes from low to high. And that's what is produced. Yes, go ahead.
How far away are the quasars that he was looking at supposed to be from the galaxies? Because he's claiming that like these glowy tendrils are like linking the galaxies to the quasars, and they're actually interconnected. So they'd have to actually be close in order to be connected, right?
Yeah,
Are they
that's
supposed to be far away.
Yeah, they're supposed to be so far away that there's no possible way that they would ever be physically connected. I mean, we're talking like quadrillions of miles between them.
Oh yeah, they're cooked.
Yeah. Yeah. So,
In a vacuum.
in a vacuum. So yeah, we go through here, just look at some different spectrums of the same images. We could see jet stream ejections intersecting with the center of the galaxy and whatnot. Just and then it's surrounded by, or it's intersected with quasars along the trail of it, and they're not supposed to be in that trail. So the mainstream astronomer would argue that, well, the quasar is actually behind the jet stream, and it just appears that it's inside of it, but really you couldn't tell. And to try to argue it mathematically, you would have to make a bunch of assumptions to prove your point, which nobody could know, because you would have to measure the exact amount of the gas or dust that is present in the measurement, and then you would have to measure the exact angle that the star is hitting that light source at, or that quasar is hitting that stream at, to get the to like quantify your distance relationship. And nobody can do that. Like they just have to assume it, but because they assume it and then calculate it, well, I mean, it can't not be true, right? They calculated it. It must be are you calling a calculator a liar? So anyway, it just kind of goes to show, when you impose your conditions on it and you calculate it, it doesn't necessarily mean that it's physically meaningful, but nevertheless they calculate. So here's some more galaxies at different frequencies here. I believe this one's in true color. So what this is instead of showing different colors for the different wavelengths of energy, they kind of use the dominant ones that are present in the measurement. So if they're looking at X-rays and gamma rays, you'll see that predominant color here. So that's why we're seeing a hard blue and orange here. Similar to this, we have a galaxy here, and then we have what is it? It's trailing off energy stream here, and leaving all these same elements and spectral lines for this. And these right here are supposed to be quasars that are not supposed to be connected to this at all. But as he goes through and analyzes this all, it appears that this was, in his interpretation of it, is that that these quasars were ejected from the galaxy based on their location and proximity and common dust elements that are too closely related to be infinite distances apart. So just more images of that. And here we can see that there's a luminous trail here connecting them this time, not just a particle one or whatever, dust or whatever. Now, next up, we have the old Einstein cross, which is said to be due to, you can kind of think of this as like gravitational refraction if it's easier to think about it. But what you, to understand this, what they would say is that this in the center here is a galaxy that has so much mass that there is a quasar behind it. And that's represented by one of these four light sources here, or energy sources. And the source that's behind this galaxy is being split into four different images.
Oh, you're lagging a bit.
Oh, okay. Testing 1, 2. How am I now?
Anyone else hearing roboting?
Yeah.
You're roboting pretty bad. I can't hear you now.
Yeah, I'm just giving it a second to see if it
Sounds
improves.
fine.
Awesome.
Yeah, you're
Cool.
gonna flush those packets.
Whew, very cool. All right. So anyway, there's a galaxy here, they say, and then behind it, directly behind it, is a quasar emitting energy, and the image of the quasar is being redirected due to gravitational forces, or due to the curvature of space-time that's bent due to the mass of the galaxy being conserved into a gravitational field. And that gravitational field is splitting the image of the star 4 different ways. So we're getting this, and this is called the Einstein cross. Now, there were several problems with this, one being that all of these are interconnected, and the distances apart that there should be no interconnectedness. And secondly, for this galaxy to have enough mass to create this effect, it would have to be the brightest object in the sky, because it would have to have, they relate brightness to mass. So when they look at this star, when they look at this galaxy here at this Einstein cross, this is actually what they consider a dwarf galaxy. It's like way past its prime in energy and output, and it's not bright enough, and it doesn't, meaning it can't possibly have enough mass to fill out the calculation that supports this. Because you can certainly put a mass in here to make this work, but this you're assuming this mass off of a brightness that isn't even present. But they need this to be the outcome. So to relate this to relativity, they're just like, well, this is how much mass would need to be done. And when you do that, this would also have to be the heaviest object in the entire universe to create this. And this isn't.
Well, just change it around and get the other side of the equation. That's how we do it. That's no problem.
Sure, we can mathemagic our way out of it.
It's crazy, dude. So yeah, this is apparently an object that's viewable in the sky, but the conditions to explain it as an Einstein cross are absurd, and they're contradicted by the center point of the galaxy that's supposed to be creating it. It's not bright enough to do it. So if this galaxy, if this was a tenable position, this object would be minus 25 magnitude in absolute brightness.
So like, you remember that whole luminosity
I'm sorry.
scale we painstakingly created and then used? Well, forget all that. This is happening. Trust me, bro.
I'm sorry. I meant absolute brightness. So that's not.
Oh.
And that's not what's there.
Was that the significance of the apparent magnitude versus true magnitude thing? Maybe that was lost on me.
Yeah, so whatever you see in the sky, right? It's like whether or not how bright it is, they say that there's a different brightness if you were to get closer to it. And they use those differences to create a distance using the inverse square law to the true source. But in relation here, they also relate brightness to density. So the brightness of this galaxy doesn't correspond to enough mass to create the brightness needed to do this lensing effect.
In answering this question, can you just take us back a few slides to the one where you show the 10 parsecs and the two magnitude scale comparisons? That'd be there.
Absolutely.
I think you're there.
Yep.
That was it. There you go. That's the one.
Yeah.
Right. So is this in relation to trying to explain something like the Einstein cross? Is that why the scale exists? That's what I was trying to figure out.
Well, it helps them in the sense that it doesn't have to be the brightness that we see it at, because they can just increase the distance to it
Right. It seems convenient
to
that
explain
this also
that.
exists.
Yeah, but when you look at it at face value in their current paradigm, if there wasn't an Einstein cross there to make them backwards derive what it would have to be, they would interpret this as a dwarf, a brown dwarf galaxy, meaning, not a lot of mass, not a lot of activity. Through this scale of changing here, using this fictitious observer for the absolute, they could just, change distances around and say, well, maybe it is that bright, but you're just super far away. But they don't even do that for that one. So they just dazzle with relativity in general. I mean, dude, if you saw somebody solving this out, would you be like, oh yeah, you know what? You're probably wrong. Like, nah, dude, he definitely carried his threes and all that. He did it right. All right, so we got some more streams here. So here's a color image from the cross in the ring situation that they say exists. Now these are from Hubble telescope, so caution or whatever. Who knows? But moving on, just looking at a couple more black and whites as we exit out here. More ejection streams and quasars, falling within the rings of gas and different emissions that are coming from a galaxy that it's definitely not supposed to be physically connected to. So in the biggest example here, there was this galaxy has a starburst core, which is just basically means it's just emitting a ton of energy, ton of X-ray and gamma radiation. And there's also a cold stream going into it, which is just, like gas and dust. So they have this like feeding system here where it's like getting in their interpretation, it's getting a source of fuel here. It's churning, it's, converting into energy and it's, blowing it out or whatever. And then in here, there's also two quasars. Now, ARP's theory, right, would put these quasars inside of the stream being ejected from the center of the galaxy. And the mainstream astronomers say, no, they're much further back. Because remember, they were equating redshift to distance. So if these have a higher redshift, they couldn't possibly be physically connected to this galaxy because this galaxy's redshift it's nowhere near this quasar's galaxy. So that's where they get into the the two hypotheses clash with one another. And then to refute one, to have more claim over the other one, the modern astronomers have to assume exactly how much helium and gas is coming out of this, and then the angle at which the star is actually at relative to this stream to where that light source is intersecting at, to create to mimic the wavelength shift as if it was in there. So as long as they can assume and calculate it out, they're good to go. And then to kind of end on the redshift significance of everything, and like how this is like a known cosmological problem. This isn't like a secret, although it's not so publicly talked about. And at the levels of academia, they all know the significance and that if anything is wrong about this interpretation, that the whole thing falls apart. So if we're going to read here from YP Varshini, who says the redshift hypothesis for quasars is the Earth at the center of the universe. What could he possibly mean here? Let's take a look at the abstract. It is shown that the cosmological interpretation of redshift in the spectra of quasars leads to yet another paradoxical result, namely that the Earth is at the center of the universe. Consequences of this result are examined. What would the implications be if the Earth was at the center versus not? I bet you they'd have to like redesign all of technology. Your phone probably wouldn't work, maybe. But we'll see what happens. What the consequences are. So moving on, we get to the end of the paper, but to kind of give a brief description of what he goes over, he analyzes 57 quasars that are uniquely visible from Earth alone. If you were in any other galaxy or on any other one of these quasars in the group, you would not see all 57 of them. So he suggests that if you arrange them in spherical shells, the Earth would be at the center of them, is the implication. So he goes on to say here, in other words, assuming that the cosmological redshift hypothesis in the group of the 57 quasars here is arranged in spherical shells, so the spherical shells representing outward, radially outward distances from the center where Earth is, and then again, if you were to analyze it if you were to transform to Mars or the center of the Milky Way or what have you, you wouldn't see all 57 of these. So he says this is an extraordinary result. Some of the possibilities that we shall consider to accommodate this may be disturbing, but we must consider these possibilities dispassionately. He's like, look, guys, there might be some biases here because nobody wants to hear this, but check it out, dog. Like 57 versus 56, or anything sub 57 is not equivalent to the Earth being at the center. And that's not supposed to happen. We're not supposed to occupy a unique position. That's why they came up with the infinite expansion with no radial center and relative distances between them. So the first possibility that we could do here is we could look at this. We could say that the coincidence in the distances could be possible if they were clustering. However, an examination of the coordinates of the various members of the individual groups show that in most cases there are no such correlation. So this explanation has to be ruled out. So they're not going to be able to say that it's just a coincidence that it just happens to work out that way for those 57 quasars. Possibility number 2, the quasars may be arranged like in atoms in a crystal lattice structure, with the Earth being at either end of the empty lattice site or at a suitable interstitial site. Should that be the case, one would expect some patterns of irregularity in the directions of the quasars belonging to a certain group. No such evidence has been found, so this possibility must be abandoned. So if you think about being like in a rosary chain or something, right, there would be like more quasars on one side of you than there would be to your right, kind of thing. So he's saying that that's not a tenable position here because there's no real clumping distribution there or unevenness. So the third possibility, the Earth is indeed the center of the universe. The arrangement of the quasar, the arrangement of the quasars in certain spherical shells is only with respect to the Earth. The shells would disappear if viewed from another galaxy or quasar. This means that the cosmological principle would have to go. It also implies that the coordinate system fixed to the Earth would have to be the preferred frame of reference in the universe. Consequently, both special and general relativity must be abandoned for cosmological purposes. So the very reasons in which these theories of physics were, which were derived to explain cosmological phenomenon, must be abandoned. Because I guess their math isn't physically meaningful. If you no longer have a need to explain the Earth's relative velocity around the sun, and for general relativity, you no longer, assuming all these conditions that they did to impose everything was clearly wrong and physically meaningless. So we'd have to abandon all that. We must also consider the two other possibilities which have been discussed in the literature and explain the apparent shifts for the quasars. The difficulty is assuming that the redshifts are gravitational is well known, and we need not repeat them here. In addition, so this is in referring to even back in 1919 when Eddington did his gravitational lensing observation on the eclipse and the stars behind the sun or whatever, or near the sun, how they were supposed to gravitationally, move in the sky. They were supposed to be offset a little bit. There was also supposed to be an amount of redshift that was calculated. So when they're referring here, as we go on to the mass over radius relationship, that's what he's referring to, deriving a redshift value based off of gravitational redshift. So instead of saying that, hey, maybe these redshifts are due to, the expansion of space or some relative velocity, maybe they're due to the gravitational influence of the planet, and as the light's escaping, it's being shifted by, the mass over the radius value. So that would be what they're putting forward. He's like, this need not be repeated here. Well, when you go over the history of gravitational redshift, which was chronicled by a guy named Norton, he has an excellent 40-year breakdown where they were trying to hone in the equations to get something that they would consider physically meaningful when they would solve how much redshift there should be for these observations. They were consistently finding no redshift that supported general relativity. So even in the time of the Eddington observation, where they were looking for the lensing, there was supposed to be a redshift observation as well to correspond that the starlight should have been also shifted by the sun's gravitational influence by a factor of the m squared, m over r, and that didn't happen. So we need not repeat them here. So like when your theory doesn't even explain anything else on the, we'll move on, sweep that one right under the rug. So in addition, there is no reason why there should be coincidences in the mass to radius value, since Z is essentially a function of mass to R for the gravitational redshift. The local Doppler interpretation of the redshift has some serious difficulties. In addition, we will have to explain why the quasars were ejected in shells. Yes, absolutely. Let's see. So we are essentially left with the only possibility, which is number 3. If you don't remember, number 3 was accepting that the Earth is at the center and abandoning special and general relativity. However, before we should accept this unaesthetic possibility, we must raise the question: are redshifts even real, bro? We wish to point out that we have proposed an alternative explanation for the spectra cited in our papers written here, which is based on sound physical principles and does not require any redshift and has no basic difficulty. And that is the end of the Prezi.
But is it even real? And if it's real, does it have any physical meaning?
Nope.
Not allowed to ask that question, that's for sure.
It's like, dude,
I
it's
bet
like
you this dude doesn't get anything published.
it's like if we want to keep relativity, special, general, and cosmological principle, he's like, we could just say redshift isn't what we thought it was. Sorry, we don't actually know that Andromeda's 4.3 billion light years or whatever away. Which really sucks because there was a TV show called Andromeda, and it was about starship that traveled to different galaxies. And that's starting to become less and less tenable as I read into the cosmological
Well,
paradigm and the math associated with it.
There was a Mass
That
Effect
really
3
sucks,
game that you went to Andromeda. No one played that.
That really sucks. You ruined my experience with movies.
That was a really excellent presentation, Alan G. I was riveted. I really enjoyed it. You've got to admit, like just from a purely science fiction-y kind of point of view, this whole cosmology that they created, it is kind of like pretty dazzling for like a person of mediocre intelligence who doesn't really have a whole lot of critical thinking, but they want to feel all sciencey, And so then they learn all this and they feel so sciencey listening to all this, and then they believe all this and they totally buy this whole, paradigm, the whole, description of their cosmology and how the universe really is and what it is and what those lights are in the sky that we see and all that. And you gotta admit, like just from a science fiction-y point of view, for some of the mediocre intelligence, it is kind of fun. I mean, they've like given explanations for everything. And then when smarter people find the holes, then they keep patching things up with stuff like dark matter and dark energy. But like I think it's kind of fun. You gotta give them the credit that the fiction itself is kind of pretty fun. Like makes you all feel all sciencey, like science and math.
Oh,
It's like the best community-funded fan fiction ever. Everyone keeps building off of each other.
Yeah, and if you go against the fanfic, then you get you get discontinued. Your services are no longer required. And that's what happened to ARP. He got blackballed from using the American observatories. So he ran Mount Wilson for like 28 years. He was the head of the astronomical program there, the head of the observatory. Like this dude was a professional, had tons of accolades and awards, very prestigious in the astronomy community. And
what did they ever say to like? It was the answer to his stuff that made them wrong. Like, was there ever a
nothing? No one
He
ever
just all of a sudden was not qualified to run a telescope.
Yeah.
Your
Yeah,
fan
so-
fiction makes too much sense. Goodbye.
he would try and publish something, and then it would get refereed because he would be like, and the ref would be like, relativity is like super true, right? Like, and like you're implying that it's not true. And he's like, yeah, that sucks, but tis the evidence or whatever. And the guy was like, no, not here, buddy.
Hence, we will not speak of it.
Yeah, man. They don't play around. If you have the credentials, like it's cool for us to talk about it on YouTube because like we don't have credentials, so no one's gonna listen. Doesn't matter, right? But like in their paradigm, this dude had all the credentials, all the math understanding, all the math to back it up, all the data, all the figures, and he was like, "Look, guys, my interpretation directly conflicts with yours, but it doesn't require any of the nonsense that you guys believe in. And everyone was like, no, we want our nonsense. And so like what they would do is they would silence him. And then sometimes like a year or so later, somebody would come up with a way to explain the observation within the confines of relativity theory. And then they would absorb the whatever the observation was as a relativistic effect due to, gravitational Hubble.
Yeah,
Holy
that's
hell.
amazing. Dude, controlling the world via control of academia. I love the Royal Society. That's the power of that. What? A conflicting worldview? Well, none of that will ever get published. No one's kids will ever learn that crap. Tell you that. Whatever idea you have is going to die with you, buddy.
Dude, that's exactly what they want, dude. So definitely check out Arp's books, because he goes over chronicling these observations for years, and then he wrote the book Seeing Red when he finally had couldn't get anything published out and was just had enough of it. So he released a tell-all of his journey through academia and the observations he was making and his thought process at the time. It's a really interesting read. Highly recommend. Don't let his ideas die with him.
What a name. Seeing Red. That's hilarious.
What if it's all in your head, seeing red?
Is that the book he made after he got fired?
Yeah.
Or whatever?
Yeah.
Okay. So
Call 'em a
cheesy.
black
Yeah, this was
cloth and
this was long after a series of being censored and then going to Britain to work at a observatory there so that he could still get star time. Dude, just love looking at the stars, bro. And they were like, you can't do it anymore here using our expensive equipment. And he was like, why? And they said, because you think differently.
Well, because you're violating our main tenet called the Copernican principle, where we all decided that we'll never be at the center and it'll never be important and everything comes from nothing, and there definitely could be no. Stop going against like the premise, guy.
And what's
guy or whatever.
and what's particularly crazy about that is that I don't even think ARP was a geocentrist. He was just saying that Redshift wasn't what they were interpreting, but
Right.
but if you were to sweep that leg out from the backbone of mainstream cosmology, then the position that everything came from nothing from a big bang becomes untenable. Now it's already untenable, but it becomes even more untenable because they don't have any way to describe why these shifts are happening.
Distances.
Yeah, these distances, like they can't have mutual exclusivity over what they're telling you. So it wasn't even about it wasn't even directly about, ARP was a geocentrist. It was about his ideas would immediately imply geocentrism. They would,
Exactly that. Yeah, that's what I was gonna say. Is that the inference from that would then immediately draw people to that giant problem. Not necessarily that he would have to have that position, but yeah. I think we should start a club for, credentialed lads who are retired and or fired and or don't care, and they can come together and exchange ideas.
So for like a layman's TLDR, this presentation was two-part mostly. You got GR and what's wrong with it, and Redshift and what's wrong with it in the expansion paradigm. What's the like GR TLDR and what's the Redshift TLDR?
So the Redshift TLDR is that terrestrially there is a relationship between Doppler shift and velocity. When you get into objects in the sky, they interpret the velocity in a way that removes it from the velocity of the object and makes it an infinite expansion of space, essentially. And, that's absurd. And if anything is wrong about that interpretation, then their whole cosmological backbone is unexplainable, because the backbone to even get the relative expansions between everything comes from an explosion from nothing. So that would become untenable. But to even get them there to kind of wrap it all together, they have to use Einstein's field equations, which require, general relativity to describe a homogeneous universe that came out of an explosion from nothing, so that as everything cooled, everything distributed in such a way that it looks like we're at the center of it. But really, if you think about it in terms of we're a dot on a balloon that has many dots on it, as the balloon blows up, all the distances between everything expands equidistantly, but it appears that nothing has moved relative to your position. So that's the way that they want us to think about it. And the only way that they could get there was by wrapping it up in all this garb. And by garb, I mean garbage. That's French for garbage.
We
Yeah, and the in the equations part about GR, weren't you saying that there was like something that it didn't math out, and some dude who went through the math and called out why it was garbage, and then they like blackballed him too?
I mean, I didn't say anything about that specifically, but it's well known that to solve the FLW or to get the solution to Einstein's field equations, which is the FLW or FLRW metric, to do that, you have to violate the conservation laws. So like, you know, there's that part of it, and they all openly accept that as fine.
What was that guy's name that pointed that out? Like originally made a paper about it and got attacked for it. There was a it was some young guy.
Oh, you're talking about
they added black holes to it and it
yeah,
destroyed it, right?
that's Stephen Crothers. You're talking about Stephen Crothers.
Yeah.
So
yes.
yeah, there's actually a separate issue with the Einstein tensor 2 that he went over. It's not even if you're not using it for the cosmological purposes for how they're doing it, just using it in general, it's not dimensionally valid because it's not derived correctly or whatever. And Einstein just put it in there anyway, and it was known as like a pseudo tensor for a long time. And then this was like a well-known thing that it was like not dimensionally valid. And then they just kind of don't, you know, stop talking about it. And then anyone that pointed it out got silenced. There was a couple Russian mathematicians that pointed that out, and then Stephen Crothers stumbled on it through his academic career when he was in his PhD candidature. And he started doing a dimensional analysis on relativity, and he found that, you know, that tensor it's not derived from the like dimensionally from the manifold, so to speak, of what they're doing. So it doesn't validly even conserve anything. It's not like I said earlier, you can't superimpose things and just like add them together. Well, like Einstein just kind of was like, I'll just do it anyway.
Yeah, Carruthers from New Zealand. Love that guy. He did a great tour and started off his lecture simply by nailing down how there is no real valid unit of measurement for, quote, space-time. And he just ran that on the board just for people to consider as a thematic element for the rest of his talk. He's outstanding.
Yeah, he's super knowledgeable in math. Great mind for it. And he breaks it down. It's so funny the way he writes about it. Like he's so disgusted with it, like with how it's being protected. He's like, this is just like what? Anyway, very passionate guy. Shout out to Steve Crothers. But yeah, he got censored too, and you know, wasn't able to fulfill his PhD candidature because his analysis led him to showing that that the equations are incorrect and that everything solved from them is invalid. So then he started looking at all the other solutions that are derived from the field equation. So like the Kerr metric, the de Sitter metric, like it basically things that describe black hole universes or a universe that has one object in it, et cetera, like all these different things. He started examining those and none of them are valid. They all describe things that are like misapplied. Like for example, they describe the radius of a black hole as a point in their coordinate system, which to correctly derive a distance on their coordinate system, you have to define it between 2 points. Using one singular point is like would be, you know, mathematically retarded. And they're like, oh my God, if we just use a single point, there would be so much gravitational force here, light would collapse in on itself. And it's like, bro, you didn't even define a distance. You only defined one part of the distance. So yeah, he does a great job of illustrating how like all those fancy equations don't mean anything, and they violate their own dimensions and premises to even try and solve them.
Man.
Like, dude, how about that, dude? A black hole isn't even a thing. It's just they were like, they looked at the point that they used to like identify the starting point for like, you know, this is going to be the distance between this thing. I forget what the word is, but there's a math term for it when you put that dot on the coordinate there, and they just use that as a single distance, dude. And then so Crothers is he And then like he doesn't just say like how it's wrong, he shows you the correct way to do it. He's like, so suppose there was a black hole, right? You would define these 2 points, take an integral over it to get the distance. And it's like they could have done it semi-correct or, you know, presentable, right? But they didn't even do that.
But it still wouldn't make his GR work.
No,
Is
it still describes
yeah.
different universes individually, etc. But they could have at least given it an actual length, like a black hole could actually. Like, so the Schwarzschild radius and all that, like none like that point at which the light can't, you know, escape. That would have an actual distance to it and not a not being defined as a singular point. Because the only reason that it's defined is that way is because it's an improper way to look at the math you're doing.
You said it fails unit analysis or something else?
Dimensional analysis.
Yeah. Okay.
So yeah. So basically you can kind of think of it as like when they solve out the equation, the gravitational field is supposed to be a result of the matter conserved or the energy and momentum, you know, conserved into it. And instead of that being the case, it's like we got all this matter and energy, like what do we do with it? And then they just like impose a field here where there wasn't one before to convert it. So it's not derived from the system dimensionally, you know what I mean? Like internally or whatever. And because they're nonlinear field equations, you can't just superimpose a thing in there to make it work. But they did, and they calculate anyway, so.
Try and stop them.
Yeah. All right. Well, if there's no further questions or comments, we can wrap up for the night.
Yo, is there any proof that GPS satellites are as high up in the sky as they say they are?
Well, slightly unrelated to Redshift, but let's see
Because they
here.
have to use GR for that, they say.
How would that prove an altitude? Oh, yeah. So for the shift of the gravitational drop off or whatever.
The
you know what though?
shifted.
You know what though? So they say that they make that correction or that there would be an offset, but they don't actually correct for it because the acceleration that you would get from the gravitational potential difference, like the acceleration of the clock, would be offset by the velocity of the clock with special relativity. So the whole 32 and 28 difference or whatever only comes out to be like a 4 nanosecond difference. So they don't actually even correct for it. And they treat the gravitational potential between the satellites and the Earth, even when they're perihelion and aphelion, the same. They treat it as like a uniform gradient.
What? I thought GR and SR added together, not subtracted.
No, one would make a clock run faster because you're getting further away from the thing that's like constricting it, and then velocity would cause retardation.
I see. Because in the receivers, there's literally no corrections for relativity at all in the software that the receivers crunch numbers on.
Correct.
I think that they claim that they tune the clock frequency before they send up the sats so that by the time it does get relativity shifted, they've already pre-adjusted it by like 10 to the negative 12th of 1 hertz or something like that. But like, how can you independently even corroborate the altitude they're at to dictate whether it would need that shift or not? You know what I'm saying?
Yeah.
Like it's already granting them the altitude.
Yeah, well, and then never mind the fact that they end up saying that that difference is offset by the motion of the thing itself, so that correction doesn't even matter.
Yeah, and then but the GPS satellites are like way too high and they move way too fast to track with radar. You can't use radar to track them. So it's like, well, how do we verify their altitude then? And then
Only from the
I feel like it's
signals,
because
only from the signals sent from them, right? You have to intercept their signals, right?
yeah, you use the GPS network's range measurement equation to verify the GPS network's satellites are where it says it is. It's like
Right, but that's a circular loop because
correct.
the satellites, the internal clocks on them, um, when they pass 2D GPS stations, they get a timing correction to them. So any signal sent will be, corrected to their coordinate system already. So when you get it on the ground and you don't have to make any relativistic corrections or anything, it's like everything's already synchronized to where you're supposed to be, and then all the corrections that the receiver makes would just be whatever it needs to be to fix the offsets that were cooked into it.
To make it WGS 84.
Right.
You know what's wild though? That literally means that somebody, I don't know how many people, probably a small handful, because they have to manage the whole network configuration of the software and stuff, but like some small handful of people somewhere in the world that manage the like super top secret GPS stuff actually know that it's actually a flat plane and they have a real coordinate system that they're transforming into a WGS 84. And that's like
Yeah.
their job.
Yeah,
They're
something
getting
like
paid
that.
for it.
Well, at least at some point somebody designed some software to automate that for sure.
Right, somebody did it. Because I mean, if they're using a not real coordinate system to represent the real world, then it has to be converted. So someone had to do that
Had to,
treatment of it.
had to have it to compare to, yeah. Yep. It gets
It's like
precarious.
what? It's like, dude, like what the heck? You're like, I can't imagine. I can't imagine like being that guy. It's like, yeah, we need you to write us some software to convert a flat Earth map coordinate system into a ball.
I don't
And
think so, man. You just use the ellipsoid, you just adopt it, and you use your hemisphere of observation to match what they pretend is also the globe. Everyone observes the same empirical hemisphere observation from that which you derive distances, coordinates, spherical models, celestial sphere, terrestrial sphere, etc. I think it's super
Yeah, but
easy. I don't think there's actually a flat Earth coordinate system anywhere that anyone's holding over or hiding. I think that you can't hide the stars. Dude.
yeah, but they have to have some basis to employ timing corrections based on true distance. Because it's all the range measurement equations all operate off real distances.
Yeah,
Because it's
like what
real,
is a
real.
what is a meridian correction out at longitude exactly?
Yeah, they would have to know the longitude latitude dependent uh distance between two longitude lines at every place on Earth for the stations to employ meridian corrections and adjust the time. Because it's going to be adjusted based on a deviation in distance from a glob to a plane, because that's what's going to affect the time of flight of the signals. Because all the signal cares about is the distance, like the straight line distance between the satellite and the ground station, and the straight line distances are going to be different on a plane.
So you're saying that Wolf and Pettit, if they were to get their hands on the data before it was adjusted for those corrections of distance, then that coordinate system in its natural form will represent the actual distance ratio that's used? Maybe.
Well, you'd have to have the real distances, because otherwise, whatever signal timing is going to be wrong, and you're not going to predict your location correctly, because the range measurement equation is where am I? How long did I take to get to you? This is where you are. And so if the distances, or if they're using glob distances, but it's a plane, and the real distances are different, they're going to get incorrect positioning. So there has to be a conversion. Even though coordinate systems can be relative, like absolute distances have to be used in the range measurement equation. Point to point straight lines. So somebody somewhere knows. I mean, sheesh, these guys have like satellites orbiting up, like at least, as far as we can tell, at least, uh, what, 50 to 100 miles. And I think there probably are hundreds of miles up. Like I do think that that's probably real, hundreds of miles of distance. I don't buy the whole like 15, 20,000 miles, but I think I think the 600 miles is probably real. At least close to that. Maybe not all of them, but there's definitely satellites up there that are extremely high up, and they would have the ability to see the topography of the land. So they definitely know.
Yeah, they know.
They definitely don't think like whoever's actually running, like I'm talking about like running the satellite networks doesn't think that they're free falling around a ball.
Probably. But
Ugh,
all right.
Give it a good press, man.
Yep.
Yeah,
we're
dude.
gonna wrap up.
Awesome.
All right, we'll be back on, let's see, Friday for community Twitter space night. Check in with Brian Sweet over on Twitter. If you're not at the community Twitter space, you're probably not a very cool person. That's all I'm going to say. I'm not going to try and pressure you into attending or anything and say that attendance is mandatory and we're taking notes and making sure everyone's, showing up and doing their part or anything. But, if we were going to introduce a social credit score for flat earthers, some people would be higher up on the credit score than others. That's all I'm going to say. And then Sunday, we'll be live with Shane presenting dams on Globebusters. The history of dams, the creation of all the dams. If you have ever looked at a magnificent dam and wondered how it was birthed, it was made over a 50-year period during the dam boom. The place where the government seized control over all the flow of water.
Dam era. Yeah.
So tune into that. And then let's see, we'll be back again I think we're going to take next Monday off. And then Tuesday, Shane will be, next Tuesday, Plain Reality will be presenting on refraction, the old terrestrial refraction, the otherwise known as the globe. Terrestrial refraction is synonymous with globularity. So he's going to be doing a nice presentation, nice breakdown on his observations regarding refraction. Looking forward to that. That'll be next Tuesday.